Perhaps the most important and enduring mystery in physics today is the question of the nature of gravity. We simply do not know what it is. We can only describe how it behaves. Our main description of gravity is the highly successful general relativity. This description and its predictions time and time again have been proven observationally to hold up. But general relativity is really a revision of Newton's description of gravity. It turns out Newton's description was incomplete, so Einstein revised and expanded on it. That may yet happen again. But what neither Einstein nor Newton did was figure out what gravity actually is. Newton himself said, and I paraphrase, "I feign no hypothesis as to what gravity actually is." But general relativity is often framed as a theory. While it is one, like Newton, it doesn't really imply what gravity actually is, rather it simply describes how it behaves. It's a description. In that framework, gravity behaves like a bending of space-time due to the presence of mass and energy. While general relativity does indeed describe it very well, and has tons of experimental proofs of it, there is a split between how gravity behaves on large scales and how it behaves on quantum scales. Basically, relativity breaks down in the world of the small, and also at the event horizon of black holes, and any effect gravity has on the quantum realm, the world of the incredibly small, is incredibly weak. And weakness means it's hard to test anything related to quantum gravity. This split resulted in some physicists looking to find a quantum theory of gravity to really nail down what gravity is. Einstein himself did this. He spent the last 30 years of his career trying to come up with a quantum theory of gravity, and he got absolutely nowhere with it. Neither has anyone since, for the most part. But that lack of progress may in fact be due to an incorrect framing in how we think of gravity. The question itself may have been framed wrong. The typical view of gravity is that it is one of the four fundamental forces of nature, and as a result of that view, we look to things like the hypothesized graviton, a particle that carries the force of gravity on the subatomic level, and the aggregate effect of it on large scales appears as a warping of spacetime. But that's not really its nature, just its effect that we see on our scales. But this may be the absolute wrong way to look at gravity. In short, it may not be a force at all, but something else that mimics a true fundamental force, but actually isn't one. Rather, it would be an emergent phenomenon. By saying emergent in physics, this just means that a phenomenon emerges from something else. One way to look at this is sound. Sound waves are an emergent phenomenon, coming out of gases or a medium. In space, no one can hear you scream, because there isn't a suitable medium for sound waves to propagate. You could even say that the human brain is an emergent phenomenon, because while it can do all sorts of things, it's really just a collection of particles like everything else. But any ideas that define gravity as emerging from some underlying fundamental something, it means that whatever that something is defines a frame that general relativity doesn't allow. Hence, an adjusted general relativity would be needed. It's technical, but in a nutshell, these types of theories violate Lorentz invariance, which observationally is held up to be true to a high degree of certainty. So the question is, how do you reframe how we're looking at gravity? One intriguing possibility is the idea of entropic gravity, and it's one that actually doesn't suffer from the problems of the rest of the emergent gravity ideas. One way past that is string theory, which is where this gets a bit shaky since we don't know if string theory is valid, and this theory may eventually turn out to require it. Here gravity emerges from increasing entropy, a product of entropy, rather than being a fundamental force. The only way to describe this is that gravity is homogeneous and predictable on a macro scale. This is what we see, our familiar, predictable gravity. But on a quantum level, it is disorderly, and does not represent a fundamental interaction like the other forces. Entropy is the concept that really just describes the reality of the universe, that within a system, over time, things move from an ordered state to a disordered state. In short, the longer you leave a system going, the more mixed up it gets. A tidy room will get messy over time if you don't do something about it. That's a very simplified way to express it, but it works. But it gets more complicated, more on that in a moment. The idea that gravity is not a force but an emergent phenomenon is something that often pops up when talking about black holes, string theory, and quantum information theory. Here there is no graviton, but a mimic of a force that comes out of quantum entanglement and the information contained in the universe itself. In short, it is a product of increasing entropy, the entropy of whatever is causing gravity, and is bound by the second law of thermodynamics because of that. But the entropy of what? And that's where it gets messy. You don't really think of this in the terms of general relativity, but this has come up before in the context of black holes. Indeed, it goes back to Stephen Hawking and Jacob Bekenstein in the 1970s, where it was found that there did seem to be some kind of connection between thermodynamics and gravity. Black holes can be described in terms of objects with temperature and entropy. This has to do with heat and black holes, but more, by the 90s, that link had been strengthened. In short, the basis for entropic gravity as an idea did not come out of nowhere. In the 1990s, the idea was floated that it could extend beyond black holes, and you could actually look at the equations of relativity in a way as being subjects of thermodynamics. So that relation between general relativity and thermodynamics itself does not yield emergent gravity. But thermodynamics as a theory is actually emergent. Basically, it's the collective behavior of a bunch of tiny things. Gravity in some ways actually looks like this as well, as a result. What are the small things for gravity? In short, the strings of string theory is the major contender right now. But it was taken further. Newton's laws could also be seen that way as well. But what is experiencing entropy in order to cause gravity? There's another way to say it. The idea here is that it's quantum information aligning, termed spin. Well, if you bring aligned masses near each other, entropy increases in this idea. That would cause the two masses to attract, and that is gravity. Complicated, but it actually works in some ways, but not in others. So this idea seems to suffer from incompleteness, or it's simply wrong. But this idea actually does tick some boxes regarding the overall mystery of gravity and what it is. First, it says that gravity doesn't actually have concrete quantum properties. In other words, there is no gravity on a small scale. It, for example, allows for gravity to become vanishingly weak on small scales, and only really becomes evident at large scales. This is what we see. And in this framework, gravity's strength decays in a linear manner with distance from a mass. One interesting aspect of this that I often hear about in the comments involves the idea of MOND, modified Newtonian dynamics, and it is also a way to reframe thinking about gravity that is related here. Basically, MOND tries, insofar as it can, to get rid of dark matter. It's no secret that the issue of dark matter is rather messy. Essentially, it proposes a modification to Newton's laws as required to account for the very large-scale effects of gravity, basically the motions of galaxies. Currently, dark matter is invoked to try to explain what we see there, but in the framework of MOND, a lot less dark matter is needed, though some have pointed out that it may not fully eliminate a need for dark matter, just not so much of it is required. That may sound convenient. It doesn't require that, at least not so much, that most of the universe is made up of matter that we cannot see any other way than through its gravitational effects. Just a smaller portion of it is. While we know that there are non-interactive particles in nature, the neutrinos, there aren't enough of them to account for dark matter by a long shot. So another type of effectively ghost matter must be invoked. So dark matter has been suspected of being a new non-interactive particle exerting gravity. If it is, then it doesn't seem to interact through the other forces. So why only gravity? Well, if gravity isn't actually a force like the others, that may be a clue why dark matter interacts through it. It's not immune from gravity, specifically because gravity is not a source. It's only immune to forces. But MOND unfortunately suffers from a lot of challenges. One of these are certain diffuse galaxies that appear to have no dark matter, or little of it. This does not match with MOND's predictions. But this is really contentious because other work on these galaxies suggested that the distance to them was being misjudged, which in turn allows them to have more dark matter than what was initially thought. MOND also doesn't really explain the observations of the gravitational behavior of the solar system, even though it would only very slightly increase the amount of gravity due to MOND. But there may be some support for MOND hiding in the solar system, and it's weird. So it's well known that some Kuiper Belt objects have orbits that aren't easily explained, which led to the hypothesis of Planet 9, that a large undiscovered planet may lurk in the outer solar system and is gravitationally affecting things out there. Mond actually eliminates the need for Planet 9, at least potentially, and if Planet 9 isn't ever found, Mond may take a step forward if the right things happen. And the good news here is we should know pretty quickly whether Planet 9 is out there or not, thanks to the Vera Rubin Observatory coming online and starting its surveys. It holds the promise to pick up Planet 9 very quickly, as in a year or two. Another issue with Mond is that galaxy clusters actually still show a discrepancy even in the framework of Mond. In short, revenge of the dark matter. You still need dark matter to explain this, just a lot less of it. But ghost matter is ghost matter. And there are other issues with Mond, basically a laundry list that is hotly debated right now in the scientific community. But back to entropic gravity. So the idea here, as I mentioned before, is that gravity doesn't actually follow the inverse square law, but instead drops linearly with distance. This results in a very tiny difference in gravity between the two, but really tiny. It's a difference of trillionths on the surface of the Earth, barely detectable. Interestingly, the entropic gravity theory actually doesn't clash with general relativity. It still holds, but in a slightly modified way. But it still works as a description of how gravity behaves as a warp in space-time on large scales. Interestingly, unlike Mond overall, the framework of entropic gravity in its main form does seem to avoid invoking dark matter, and instead says that gravity isn't a force at all, and instead is a result of quantum effects, and constitutes a kind of positive dark energy. Yes, dark energy is still there in this. Dark energy does not go away here even if you get rid of dark matter, dark energy remains. This is one of those things that could get messy because if entropic gravity turns out to really reflect how the universe works, and all its implications mesh together, it's going to require a lot of rethinking in cosmology. In a way, modern cosmology has become reliant on dark matter because it explains a lot of observations. Dark matter is integral, even though we really don't know what it is. Without, it's back to the drawing board for a large amount of astrophysics. But experiments are being devised to test entropic gravity nonetheless. Another way to look at this comes from Eric Verlinde, a proponent of entropic gravity who is solidifying the formulation of it. So think of it like this. Say gravity is an emergent phenomenon instead of a force. It's not fundamental. But more, it actually in a sense implies that gravity doesn't actually exist. At the same time, however, entropic gravity ideas have been subject to very heavy skepticism within the scientific community, with what tests have been done so far coming up contradictory. In one study, observations supported it. In another, it wasn't supported. And there's also the peripheral evidence of the existence of dark matter in other areas of cosmology that the hypothesis doesn't really cover very well. But again, the subtlety and weakness of gravity at the scales needed to test entropic gravity makes it extremely difficult to test. And given its connections to string theory may make it a theory dependent on another theory that we aren't certain is correct. But entropic gravity does represent the current best shot so far as reframing gravity not as a fundamental particle interaction, but something else entirely. Thanks for listening. I'm futurist and science fiction author John Michael Godier, currently reflecting on a lifetime of fighting gravity, and it never ends. Even if you leave Earth and sit weightless in space, you are still being acted upon by the gravity of distant objects. It's everywhere, never a break. It's like the universe's equivalent of taxes. And be sure to check out my books at your favorite online book retailer and subscribe to my channels for regular in-depth explorations into the interesting, weird, and unknown aspects of this amazing universe in which we live.